Now let's shift gears and look at the other part of the Environmental Control and Life Support Subsystem, or ECLSS. We know space is a tough place to live and operate for equipment and even more so for people. If people go into space, they need to bring almost all of the things we tend to take for granted here on Earth. They need oxygen at the right pressure, water for drinking, hygiene, and humidity, food to meet energy requirements, and waste management so they're not overwhelmed by trash and other smelly stuff. In this section, we'll look at how the ECLSS does all this. Earlier in this chapter, we reinforced some of the long-term challenges of living in space, such as charged particles, radiation, and freefall. Here we can see the inputs and outputs associated with people, represented by Jerry the rocket scientist. Like any other system, humans take some amount of input, process it, and produce output. We must supply each input and carefully consider how to handle the outputs. Inputs include water, food, and oxygen. Outputs include urine, perspiration, carbon dioxide, and feces. Notice the balance of inputs and outputs at the top of the picture. If things aren't in balance, you'll gain or lose weight. At sea level, the air we breathe is about 21% oxygen, 78% nitrogen, 0.04% carbon dioxide, and the rest consists of trace gases. When we breathe, our lungs take in all these gases, and the oxygen gets used to burn other chemicals as part of our metabolism. Within our lungs, oxygen transfers to the blood in exchange for carbon dioxide. By exhaling, we dump carbon dioxide back into the air around us. On Earth, plants eventually absorb this waste carbon dioxide and exchange it for oxygen, and the process continues. In space, it's not that simple. In space, the life support system must provide a breathable atmosphere, which includes oxygen at a high enough partial pressure to allow for comfortable breathing. Without that, astronauts could not survive. The term partial pressure refers to the amount of the total pressure accounted for by a particular gas. The symbol for the partial pressure of O2 is ppO2, and we're quite comfortable with the ppO2 at sea level. After becoming acclimated, people living at high altitudes, about 6,500 feet, show little discomfort with a lower partial pressure. The Space Shuttle's life support system maintains a partial pressure of oxygen close to Earth's sea level standard at ppO2. You can see here a European Space Agency astronaut wearing a suit used to maintain the correct atmosphere around the astronauts in case there is a loss of cabin pressure during launch or re-entry. Since oxygen is all we really use when we breathe, why not just use all oxygen in the crew cabin instead of air? When the partial pressure is too high, oxygen is actually toxic. Also, a pure oxygen environment can make it far too easy to start dangerous fires. This slide shows America's first major space tragedy, and it illustrates why we no longer fly with a pure oxygen environment. On January 27, 1967, on Launch Pad 34, Edward White, Virgil Gus Grissom, and Roger Chaffee died in a fire during a routine pre-flight test on the launch pad. A spark started a fire in the Apollo 1 capsule that quickly got out of control, killing all 3 astronauts. Heroic doesn't begin to describe these men who, even though they were fully aware of the risks involved, still chose to head the mission for the cause of advancing our understanding of space. The proper mixture and pressure of gases is important for thermal control as well. As we learned in the last section, convective heat transfer using the cabin's atmosphere can be used to cool electronic components. Circulation of the cabin's atmosphere is also important to ensure good mixing of the atmospheric gases in freefall. Another key concern related to atmospheric pressure is that whenever astronauts do EVAs or spacewalks, they must leave the crew cabin atmosphere and use a spacesuit that provides all the comforts of home, including oxygen at the right partial pressure. Unfortunately, if the total pressure in the spacesuit is near sea level conditions, it would be so stiff astronauts wouldn't be able to bend their elbows or close their fists. Imagine holding a tennis ball and trying to squeeze it tight. For this reason, some spacesuits operate with a total atmospheric pressure lower than the cabin pressure. This pressure level allows the suits to be flexible so astronauts can more easily move around and work. However, this means lowering the cabin pressure several hours before a planned EVA so astronauts can get used to the lower pressure before stepping into the suit. But problems can arise when people change from higher to lower atmospheric pressures. People may experience the bends we often associate with scuba diving. The bends occur when divers move too quickly from high to low atmospheric pressures. Scuba divers breathe in air. When a scuba diver is deep underwater, the pressure is higher, so more of the nitrogen in the air gets dissolved in the bloodstream. If they come up too quickly, that nitrogen can form bubbles in the blood, causing severe pain in the joints and even death. To avoid this problem, spacesuits use a pure oxygen atmosphere with a partial pressure sufficient to sustain life. Before going outside, astronauts breathe pure oxygen for 3 to 4 hours to purge any nitrogen from their bodies so they don't get the bends. Astronauts must take everything they'll need with them when they lift off. The space shuttle's atmosphere must be created and sustained with the resources on board. The shuttle carries liquid oxygen and nitrogen into orbit, and the life support system processes these raw supplies to provide the proper atmosphere. To do this effectively, astronauts rely on an efficient closed-loop atmospheric control system. Can you remember the difference between open-loop and closed-loop control systems? If not, go back to the section on control systems so you understand the concept. Now, let's discuss other necessities, such as food and water. Just like you, astronauts get hungry and thirsty after a hard day in space and want something tasty and nutritious to eat or cool and refreshing to drink. But getting into space is very expensive, so we must determine exactly how much food and water to bring along. Too much and we waste precious cargo mass. Too little and astronauts go hungry. The average person needs about 2 liters of water per day to stay alive. A person needs another liter or so to prepare and rehydrate food. We also use water for personal hygiene, washing, shaving, and so on, as well as doing laundry and dishes, can add up to 20 liters per person per day. But doing laundry and washing dishes require too much water, so the International Space Station and Space Shuttle don't have washing machines and typically use only disposable dishes. Here we can see an astronaut washing his hair in space. The average person requires about 29 calories per kilogram of body mass per day to maintain their present weight. This means a typical astronaut who is about 70 kilograms needs at least 1,972 calories per day, and even more when strenuous spacewalks occur. Space food has come a long way from the peanut butter and orange drink called Tang used during the Gemini missions. Today it's become trendy for celebrity chefs to adapt their recipes for spaceflight. The emphasis now is on providing fresher foods and to save on mass, volume, and improve packaging that won't create as much trash afterwards. Much of the food for space missions is dehydrated or freeze-dried to reduce volume and mass. But for short-term missions and for eating in the first few days of any mission, astronauts may take fresh fruits and other perishable items. Typically, each astronaut needs at least 2 kilograms of food per day. Water for the space shuttle comes from fuel cells that create electricity and water from hydrogen and oxygen. Because of the restrictions on volume and mass, the ISS requires water and food to be delivered by Russian Progress robotic spacecraft, or the space shuttle. It needs supply flights every few months to support its crew of 2 to 3 astronauts. You can see here a transfer of materials to the ISS from the European Automated Transfer Vehicle. We provide astronauts with food and water, but what happens to all that waste in the form of urine, feces, and carbon dioxide? Well, we need to dispose of them, and we're going to learn how. Collecting, packaging, and disposing of these wastes are one of the biggest jobs of the life support system. Urine and feces pose health risks as well as odor problems. Carbon dioxide creates a subtler problem. Unless carbon dioxide is removed from the atmosphere, it can increase heart and respiratory rates, change body acidity, and eventually reach fatal concentrations. A frequently asked question is, how do the astronauts go to the bathroom in space? The answer is very carefully. This is the space shuttle's toilet. Remember, in orbit, everything is in free fall. The spacecraft, the astronaut, as well as the feces and urine are all falling at the same rate. Feces in free fall can be a problem, so the space-qualified toilet uses a suction system to pull waste materials away from the person using it. Astronauts receive at least 20 hours of toilet training before going into orbit. Compared to the toilet arrangement, removing carbon dioxide from the atmosphere is much simpler and far less messy and smelly. For example, on the space shuttle, replaceable canisters like the one shown here, containing charcoal and lithium hydroxide, filter the air. Lithium hydroxide chemically reacts with the carbon dioxide, trapping it in the filter. The lithium hydroxide canisters must be changed out regularly, and because they get saturated, the astronauts must leave Earth with an ample supply. If we intend to go on long missions to other planets and live on them, we must rethink our approaches to life support on the shuttle or space station. For example, we can't afford to carry all the food, water, and lithium hydroxide canisters we need for a mission that might last for 2 to 4 years. And we may have difficulty sending supply ships often enough to resupply food and water. Scientists are investigating life support subsystems that can retrieve and recycle water, which is the heaviest item. One limited approach to this idea is to retrieve gray water, which was only used for washing and rinsing, and reuse it for things other than drinking. So for future long-term missions to the Moon or Mars, we must develop a life support system that can provide food, water, and atmosphere in a closed loop without using stored water, food, and air. Here we see Jerry the rocket scientist with the closed-loop life support system. Bioregenerative life support subsystems would let us close the loop completely and recycle all human waste into food, water, and oxygen. Although this may not sound too tasty, it would mean that we'd have to pack much less to take along with us. We might grow our own food and provide our own water by processing materials found on other planets. Here you can see astronaut Peggy Whitson with shuttle-grown soybean plants. We might also be able to live off the land. Mars, for example, has deposits of ice that we could collect and melt for water. We could also separate the water into its basic components, hydrogen and oxygen. We could then use the oxygen to refresh an artificial atmosphere. We could also use the hydrogen and oxygen as propellants to get back to Earth. So many possibilities exist here, but this is one of the challenges of future space flights. Remember, you could be one of the scientists or engineers who help meet this challenge. Now that we understand some of the basics of the thermal control and life support subsystems, we'll look briefly at the inputs to the overall mission design process. Then we'll review some of the testing requirements spacecraft must go through before launching into the harshness of space. We also have to think about how we put everything together through systems engineering. In our overall design process, we found that we need to define subsystem requirements and constraints. If a spacecraft will have people on board, we must provide all necessary life support systems discussed earlier. We have to provide water, air, food, and waste management for the number of astronauts on board. We simply multiply the amount of consumables required for each person by the number of days in our mission to create a life support budget. Using this life support budget, we can begin designing the systems needed to support human life. If we're designing a robotic mission, we don't need a budget for life support, but we still need to create a thermal control system. Why is that? If you said because we have to protect our spacecraft's components, you'd be right. Once we have a set of good requirements and constraints, we can begin analysis and design. Recall in the last section, we discussed the concept of thermal equilibrium. This concept is simple, but important, so we're going to show it again here. In order to maintain this state, the heat output must balance the heat input plus internally generated heat. This is one of the biggest challenges for the thermal control system, especially if we try to do it for all mission conditions. For example, during ground testing, pre-launch and launch, as well as on orbit. Keeping things cool in full sunlight may be no problem. Keeping things warm during an eclipse may be no problem. But keeping things at the right temperature at both extremes and everything in between will likely require detailed investigation. For example, the thermal analysis results shown here display the solar array temperatures in degrees Celsius expected during a certain mission phase. The blues are cold and the reds are hot. Thermal engineers need to work closely with the engineers from all other subsystems to make sure the spacecraft's components stay within proper temperature ranges. A detailed thermal model is the best method to predict temperatures at every place in the spacecraft. This is done by dividing the system into a series of nodes. A thermal node can be any payload, subsystem, or even part of the structure that has unique thermal properties. The spacecraft thermal analysis method has us connecting all of the nodes as shown in the figure here. We can then tackle this big problem one small piece at a time by looking at each node individually to define the unique thermal properties of each one and understand the heat conduction and radiation between nodes. Once this is understood, we can then use computer analysis to determine overall system temperatures when all the nodes are connected in different environments, say full sun or during eclipse. Next, we must test it to ensure the spacecraft can meet all requirements. Will the batteries be too hot or too cold? Will the onboard radio be at or near room temperature? The computer analysis we just looked at will make predictions, but we want to be sure those predictions are right before launching our expensive spacecraft into space. If we find problems there, it will be too late to fix them. So, to test our predictions, we typically put the entire spacecraft into a large vacuum chamber and measure temperatures at various points while we increase and decrease the chamber temperature to simulate conditions in space. During these tests, we measure the spacecraft's temperature and compare the results with our predictions. If the test results don't match our analysis, we try to figure out why. We may also do a thermal cycling test by placing the spacecraft in a chamber like the one shown here, where we can control the temperatures in the chamber from high to low and measure the effect on the spacecraft's temperatures. We often put the spacecraft in a thermal vacuum chamber, like the one seen here, to see if the spacecraft can survive the ranges of vacuum and temperature in space. This photo shows a larger, more expensive thermal vacuum facility. Once we've verified that the spacecraft has met its requirements, we can get ready to ship it to the launch site. Let's review by trying to answer the questions on this slide. We covered a lot of material in this chapter, so you may want to review the checkpoints and key concepts at the end of the chapter before you start the activity. In this lesson, we focused on the environmental control and life support subsystem, which we refer to as the ECLSS. We learned the ECLSS must provide a livable environment in the harshness of space. The tasks of the ECLSS are divided into two problems: thermal control and life support. We looked at ways to meet the thermal control demands. Then we examined challenges caused by placing fragile humans on board. Finally, we studied some of the major systems engineering issues of ECLSS design. A spacecraft consists of many subsystems that must work together to keep the spacecraft functioning properly to meet overall mission objectives, requirements, and constraints. The ECLSS is one of those subsystems that provide a livable environment to keep people and machines healthy and happy. Now that we have a good understanding of spacecraft, payload, orbits, and trajectories, we're ready to learn about propulsion and launch systems, how we operate spacecraft and use them to meet our overall objectives.